my dear children, once again welcome to our physics class. Hope you all are fine over there. Children, in the previous session we had discussed about lenses. We discussed the ray diagrams and also the image formation of both concave and convex lenses. You should remember all the ray diagrams. All of them are very important. You should remember the image positions for the corresponding object positions. Today, let's discuss about the lens formula, magnification, and also the power of a lens. So the sign convention and the magnification formula and mirror formula are almost similar to that of spherical mirrors, only slight modifications are required. So just be attentive throughout the sessions. Let's get started with today's session, my dear children. Let's continue with the lenses. So today we are going to discuss the sign convention of the lens first. Sign convention for spherical lenses is same as that we followed in the spherical mirrors. We apply the rules for sign of distances except that all measurements are taken from the optical center of the lens. According to the convention, the focal length of a convex lens is positive and that of a concave lens is negative. So you must take care to apply appropriate signs for the values of u, v, f, object height h and the image height h, I. Okay, so the same rules we are following here too. Horizontal distances to the left of optical center is taken as negative. So consider this is your convex lens and this is optical center. Here you have f1, here you have 2f1. Here you have f2, here you have 2f2, and the distance from optic center to the focus will be focal length f. So what will be the distance between optic center and 2f1? It will be twice that of the focal length. Here also the distance between optic center and the second focus also will be the focal length. At the same time, the distance between optic center and the distance 2f2 or point 2 of 2 also will be twice of the focal length. So a lens has two foci and both the foci will be at the same distance from the optical center. That means a lens can have only one focal length. So here horizontal distances to the left of optical center is negative. That means if we consider this as our convex lens and this as our optical center, all the distances taken to the left of optic center, that means horizontal distances taken to the left of optical center will be negative, and all the horizontal distance taken to the right of optical center will be positive. And what about the vertical measurements? All the vertical distances above the principal axis. So this will be our principal axis, and anything above the principal axis, that means this direction, all this direction is taken as positive. And all the vertical distances below the principal axis, this distance, all the distances, vertical distances below the principal axis is taken as negative. Okay, so this is same as the Cartesian coordinate system. Origin is replaced by the optical center of the lens. The same sign convention we follow in the case of concave lens too. Okay. In mirror, we discussed about the mirror formula. In lens, we have to discuss about lens formula. So what is lens formula? Lens formula is 1 by f is equal to 1 by v minus 1 by u. Do you remember the mirror formula? What was mirror formula? Mirror formula was 1 by f is equal to 1 by u plus 1 by v. Here the lens formula is 1 by f is equal to 1 by v minus 1 by u. So that is the difference. U, v and f have the same meaning as that in the case of mirror. What is f? F is the focal length of the lens and v is the distance between the image and the optic center of the lens, and u is the distance between object and the optical center of the lens. Okay, so in this figure you can see the v, u and f. So here this distance is f, What is F? F is the distance between optic center and the focus F2. Okay. Then this distance is U. What is U? U is the distance between optical center and the object. Okay. This is the distance V, and V is the distance between optical center O and the image A dash B dash. Okay. Then in the case of convex lens, we are more concerned about the focus on the right side of the lens. That means about this focus, because all the refracted rays passes through that region. So in the case of convex lens, we will consider this focus F2, and it is on the right side of the optical center, so it can be considered as, or it can be taken as positive as per a sign convention. So the focal length of convex lens will be positive. At the same time, the focal length of concave lens is negative, because in the case of concave lens, we are more concerned about the focus to the to the left side of the optical center. Okay, so this is the lens formula. 1 by F is equal to 1 by V minus 1 by U. Then here, this is the image formation in convex lens. We had discussed about this ray diagrams in our previous session. Here, what will be U? We can just mark U. What is U? U is the distance between object and the optical center. So this is optical center, this is object, and this distance will be U. U is negative. So in the case of lens also, we can take U as negative always. Then, where is the image here? Image is not specified. Image is somewhere at infinity. So anyways, image will be formed always to the right side of the optical center. So the image distance, we don't know the exact position of the image. So the image distance is taken as infinity, and it will be positive itself. Now here in this case, in this diagram, where this is the object, AB is the object, so this will be the distance U. U, it is to the left side of the optical center, so it is negative. U is negative here. Then which is our image? A dash B dash is our image. It is also located to the left side of the optical center, and this is the image distance V, distance between image and the optical center. It is also taken as negative. Why? As per sign convention, V is or image is to the left side of the optical center. Okay. Next, in this case, where will be U and V? So here object is at infinity. Anyhow, object will be to the left side of the lens. So object distance U will be taken as infinity, or it will be negative. And where is the image? Image is also formed on the left side of the optical center. So this is the image position. Image is formed to the left side of the optical center. So V is also negative here. V is also negative here. Now consider this diagram. Here, this is our object AB, and this is image A dash B dash. So this is V. Both U and V are situated to the left side of the optical center. So U and V is taken as, both U and V is taken as negative. Okay. And in the case of concave lens, it's very clear. We are more concerned about the focus F1. That means which is to the left side of the optical center. Hence the focal length of concave lens is taken as negative. It's very important concept. You must always remember this. Focal length of concave lens is taken as negative. Okay. Next we can discuss about magnification. So the magnification produced by a lens is similar to that for spherical mirrors. Magnification is defined as the ratio of height of the image to the height of the object. It is denoted by the letter small m, and two equations are there to find out magnification, which is the first equation. Magnification m is equal to height of image by height of object, that is hi by hu. In case of spherical mirrors, magnification was minus v by u, but for lens it is just v by u. So which are the two expressions to find out magnification of a lens, magnification produced by a lens? It is m is equal to height of image by height of object, and also m is equal to v by u, where v is the distance between image and the optical center of the lens, and u is the distance between object and optical center of the lens. So here also magnification helps us to obtain an idea of how bigger or how smaller an image is with respect to object. Next, we are moving on towards the last concept of this chapter, that is power of a lens. So what do you mean by power of a lens? We have already learned that the ability of a lens to converge or diverge light rays depends on its focal length. Okay, so how can we prove that? Consider this convex lens, and this is the focus of that convex lens. This is the optical center, and a light ray is incident here, and this light ray, as per the rule, passes through the focus. So this is the actual path of the light ray, but due to the presence of the lens, it bends like this. So what is the degree of convergence here? It is converged. The light ray is converged to a point on, that means on the focus. So this is the degree of convergence. This angle gives us the degree or measure of that convergence. Now consider another focus. Now consider another convex lens, and its focus is situated here. Again the same parallel rays incident to on the lens, and this ray of light, after passing through the convex lens, it must pass through focus, and this ray should go like this, supposed to go like this. Due to the presence of the lens, it has converged like this. So this angle gives us the degree of convergence here. Now look at the first and second figure. What is the difference between these two figures? In the first case, this was the focal length of the lens, and in the second case, this is the focal length of the lens. So in the first case, focal length is less, right? But the degree of convergence, that means this angle, was more. At the same time, in the second case, focal length was more, but this angle or the degree of convergence is less. And you know, this degree of convergence or divergence is nothing but power of a lens. Okay, so the power of a lens is nothing. It is the ability of a lens to converge or diverge a given light ray. It is the measure of the degree of convergence or divergence of a lens. And it is very clear that this convergence, the degree of convergence or divergence of a lens, is inversely proportional to the focal length. That means the power is always the reciprocal of focal length of a lens. Okay, so the degree of convergence or divergence of light rays achieved by a lens is expressed in terms of its power, and power of a lens is defined as the reciprocal of its focal length. Power is represented by the letter P. And what is the equation? Power P is equal to 1 by focal length. And this focal length should be always expressed in meter. Otherwise, we won't get the actual power of that lens. Okay. So, the power of a lens is 1 by focal length, and that focal length should be substituted in meter in the expression. Unit of power is diopter, capital D. And what is the power of a concave lens? Is it positive or negative? That is the next question. Children, as you know, focal length of a concave lens is negative. So power of a concave lens also will be negative. Power of a convex lens is positive. Why? Because focal length of convex lens is positive, and you know power is the reciprocal of focal length. Okay, so that's all about power of a lens.